Morning, everybody. How are you guys? So excited next week is spring break. Me too. All right, well, I'm going to give it just one more minute here, and then while people jump on, and then I have a few announcements to share, and a couple things to talk about, and then we're going to jump into chapter 7. How about this weather this week? I'm really enjoying it. It's really good. Well, any questions from any of you guys? Yeah, wonderful weather. Y'all doing okay? How did that anatomy test go? Maybe some of you didn't have one, but I heard there was a big anatomy test yesterday. Not the best. Awful. Why was it so bad? Was it like a midterm or what? Okay, for me, good. Had a lot of information, just a lot of content, plus a bone practical. Somehow I managed to make it through college without ever taking anatomy. But there's a lot. Well, I hope it went okay for you guys. Join us with your video, please. It helps me teach when I see your faces. I mean that. Thank you, thank you. Okay, well, I am gonna get into a few things. What do we got this morning? Some announcements that I have. I posted the exam 2 key, so you can get on and dig through that and look over it. It has a lot of information about how I worked, different problems and things like that, or how they should have been worked. There was I'm missing lone pairs on one of the Lewis structures. If you looked at the key, I had somebody email me about it. There's a fluorine on, I think, D, A, B, C, D. Those were the Lewis structures, and on the last one, so I'm going to go back and fix that. But if you notice that, yes, there should be lone pairs on any halogen. Should have lone pairs. So some of you forgot lone pairs on your halogens, but I'm going to fix that on the key. And then I wanted to address the whole naming question issue. Hopefully that was addressed pretty thoroughly from the email. But in case you haven't read your email and you don't know what I'm talking about, somebody check to make sure you're muted. I'm getting a little feedback. We had a naming question. I'm just going to share over to my iPad, in fact, really quick to talk about this. So you were asked to name, I think it was these 3 molecules. And then P3O7. Okay. So I ask you to name these, and we've learned a couple of ways to name molecules. We learned how to name ionic compounds, and then we learned how to name binary compounds. And those are the only ways that I've taught you. So there's other ways to name molecules, especially once you get into organic chemistry. They have really complex naming systems, but we've not covered any of those. Also, I mentioned in the email that molecules have common names. For example, CH4, we would call CH4 carbon tetrahydride, but the common name of it is methane. It's a fuel. Maybe when you go to grill or something, you go by a propane tank, okay? Propane is C3H8, okay? Tetracarbon octahydride. So there's different names for it, but I've not taught you any of the common names. So when I started seeing things like butane and hydrazine, I started to turn my head a little bit. because we just didn't go over those names. And those names are correct. They're not wrong. But to me, that's a sign that some people use the internet. Now, here's the deal. I've had emails from students as well that actually did know the names of those. And they showed me notes from like a high school chemistry class or a transitional chemistry class they took before mine. And so they did know butane. And so they put butane on there just because of that. I had some people who put hydrazine and butane. I had some people who just put butane. But then what I thought was most interesting is you put the common name for these two, but then you took the time to put the correct name for the last one, triphosphorus you lose the A, oxide, heptoxide. So why would you name the last one correct, but then not name the first two the same way with the same naming system? So that was definitely what was indicative to me that outside resources were used. And I'm not furious. I do think it's a shame. I want you guys to do the exam adhering to the academic integrity policy that you sign. And I want you to walk away from this class having learned this stuff. I know some of you think I'm never going to use this class again. If you're going to nursing school, if you're headed that direction, you will. Okay, so I genuinely hope that you walk away from this course having something to show for it. But anyways, just so you know, I gave anybody who put those common names a 0 on that question. It was worth 6 points. And just so that you've heard it directly from me, if anybody has an incident in the future where I can tell the internet was used in some way on the exam, it will be a 0 on the exam. And I don't say that joyfully. I hate these situations. I hate them. They're no fun for me. So please, please don't put yourself in that spot again. I can usually tell on some things, but anyways, that's really all I have to say about it. If you have any questions about it, I'm approachable on this stuff. You can shoot me an email. We can talk about it. Okay. I'm not saying you're going to change my mind on anything. But anyways, there's that. If you have any questions, send me an email. Other things to know is the Chapter 7 homework is already posted on Mastering Chemistry. So once we get going today and Thursday, you can get started on that. It's not due until the Monday after spring break. So I encourage you to knock it out this week if you can, or as much as you can. That way it's not lingering over your head on spring break, okay? Because I guarantee you 90%, not 90, that's a high percent, maybe 80, maybe 70%. A lot of you are probably going to wait until after spring break, and don't do that to yourself, okay? Hold on, we got some in the chat. When you get time, would you go over the lab question 3? Is that for Gabby, the lab we did yesterday, the enthalpy practice lab? Okay, we have some students that haven't even done it yet. So I can send you an email about that one, Gabby, but I'm not going to go over that one in front of everybody yet because we have some people who have the lab on like Fridays and stuff and just haven't gotten to it yet. Or if you have a question about that specifically, you can hop on my office hours right after this. Okay, so Chapter 7 homework and then lab grades. I wanted to talk about this. I agree. I've had students comment and mention Blackboard is the most frustrating part of an online chemistry question. Anybody agree with me? Typing in your answers, it sucks. I hate it. I hate it for you guys. Just so you know where to stand on that. And I really try to do my best to allow the answers on Blackboard to accept a range so that, the last freaking decimal doesn't necessarily matter. But I've noticed a few people have emailed me and said, hey, I missed a few points on my lab and I thought I got the questions exactly right. I'm wondering if those ranges aren't as big as I thought when I set them. So if you have any questions on your lab grades, like I literally just missed, like I checked the students, I forget, I don't know who it was, it doesn't matter, but they had put let's say the answer was like 91.07 grams. They put 91.06. Well, I want Blackboard to accept that as correct, right? That's what I want. So when I set the answer and I choose, how I want it to work, I want that to be correct. And I noticed there was one that was really close like this and it counted it wrong. So that's infuriating to me. So if you notice that on any of your assignments, I'm just saying there's like 140 of y'all. And so please just double check your lab grades when you see them. And if you have any questions on them or it counts you wrong on something like this, please notify me immediately so I can correct that for you. I'm happy to get points back on those things. I don't want anybody to be counted wrong for stuff like that. Any questions from you guys on any of this? All right, well, that's it. We're going to jump over to chapter 7. Now we're going to talk about something fun. We're going to talk about hiking. Now that the weather's warming up, you should definitely get out. Now that we're getting some greenery back in Arkansas, it's the best time to go hiking. Anybody been to kind of North Arkansas area? Anybody been trout fishing on the White River? This is a picture of the White River, actually. And so really popular place to go trout fishing and stuff, or maybe other kinds of fishing too in Arkansas. But anyways, this is Calico Rock, is specifically the little city that you'll pass through. Really beautiful. This was taken in the fall, like in October-ish. And so it's kind of this kind of rock cliff structure here. And you can drive up to it. You don't have to hike there. You can kind of park and then just walk out over it. And it's really, really cool. It's really fun. You get just a really pretty view of a big area. So I will tell you though, if you go in the fall to this area, be prepared because it's tarantula mating season in Arkansas. I bet you didn't know this. I hate spiders. I hate tarantulas. I never want to touch one. I don't want to see one. I'm not even looking at this picture if I can help it. But every time we've gone up in this area in the fall, we see tarantulas. Like we see them on the road. We see them driving in our car, and my husband always stops the car and pulls over. And I'm the one taking this photo, so I tried to stay as far away as I could. But anyways, I'm gonna zoom in for you. You guys want to see it up close? It's disgusting. Yeah, sorry. Okay, moving on. Chapter 7. So preface chapter 7 really quick. We're going to cover as much as we can, but here's the deal. I don't want to rush through it. There's a large audience of you guys. A lot of you tend to hang okay, and then some of you, really want me to slow down on stuff, and I am going to try to honor that best I can. I'm going to try to go as slow as I can for you. But I usually allot 3 lecture days for chapter 7. And because of the snow day and all of that, I told people in lab yesterday, I had to cut a day somewhere on the schedule. And I cut a day of chapter 7 lecture. So I don't know if there's just some material that I'm going to cut from the exams period, but I'm just giving you a heads up and a warning. I may have to do like 2 or so 10-minute, 12-minute lecture videos on the end of all this, pending how far we get, okay, to set us up for like chapters 8 and 9. So just giving you that warning. I don't like to do that, but I may have to with this chapter. Chapter 7 is all about understanding energy that is associated with chemical reactions, okay? And how energy affects the rate of chemical reactions, how energy affects if chemical reactions are going to happen or not, the result of chemical reactions. So you see these pictures here are the result of some chemical reactions. Anybody know what this picture on the left is?
It's like an explosion went off.
Somebody say that again?
I say it looks like that explosion went off.
Yeah, a huge explosion. Okay, so this was a nuclear reactor over in a city called Chernobyl in Russia. And they had this huge nuclear reactor, and one of the reactors exploded. Something went wrong in the core, and this was the aftermath of it. And then sadly, even beyond this, a ton of radiation was released out into the air. So everybody had to evacuate the town. Yeah, really awful stuff. This was like back in the 80s, I want to say. Or I could be wrong, but it could have been earlier than that. But anyways, for a while, people were really timid about moving forward with nuclear energy because of stuff like this. Because if an explosion happens, obviously there's a lot more damage that's done than, say, other sources of energy. But anyways, that's one example. Very powerful chemical reactions. Here's another one. Obviously, you can see there's a lot of heat associated with this chemical reaction, the friction from the tire and the road. And then you see the flames and the fire and just the immense amount of heat. So some chemical reactions release a lot of heat. Some chemical reactions release other kinds of radiation. And these are all sources of energy. So we're going to talk about a few different sources of energy today. So I wanted to ask you, What are the main forms of energy? How many different forms of energy can we think of? You can type it in the chat. You can shout it out. Solar. Thank you. You may see from some of these pictures. So we got solar energy. There's a few different forms in my pictures. Any other kinds of energy? There's definitely more than this. Kinetic. Yes, Gabby, kinetic, I think in a couple slides, we're going to talk about kinetic and potential. Those are kind of the two umbrella things. So I'm not actually going to write that one down on this list. But kinetic is a form we are going to talk about. Nuclear, yes, Bailey. Yep, nuclear energy.
Wind, waves.
Wind energy. So I would call this these turbines down here. They're spinning because of mechanical energy. So the wind is pushing them and it's harnessing that energy and it's turning it into, what do we use these? Like you probably drive on the interstate and you see huge fields with all these wind turbine things. We use the wind, energy from the wind to make what kind of energy? Same thing that hydroelectric dams do. They take energy from moving water and they make what kind of energy? There we go. Thank you, Riley. Electrical. Okay. Nuclear, mechanical, solar, which is, some people might say electromagnetic energy is the solar energy from the sun. And we got chemical energy. Okay, we also have thermal energy. This is the heat that we were talking about. 1, 2, 3, 4, 5. So that's a pretty good list. It's not everything, but that's going to get us going. Okay, so maybe you can think of some other kinds, but I think that's a decent list for today. So speaking of the human body now, because that's kind of what we're all more interested in, what kind of energy does our body use? Our bodies run off of kcals, so that's the units for energy. Good job. There we go. Thank you, Grant. Chemical. Okay. Yes, Tia, ATP, which has chemical energy in ATP. Anybody know how our body makes ATP? What the systems or the processes are called? There's a few tied together. Okay, it's all part of our metabolism and it does happen in our mitochondria. That's correct. So the sum total of our metabolism, that's all the chemical reactions that, yes, there we're getting specific. So our metabolism includes things like, we'll write this down. We've got glycolysis. Anybody heard of glycolysis? That's how you take glucose, okay? Everything ultimately, not everything, but a lot of things are broken down into glucose. And then our body takes molecules of glucose, breaks it down further in the process of glycolysis. Then we have the Krebs cycle, where the glycolysis feeds the Krebs cycle, essentially. Then the Krebs cycle is what feeds something we call, I'm going to abbreviate, it's called oxidative phosphorylation. Okay, and I'm not going to go into any of this, but these are all related, and all of these together, this is our metabolism. And this is how the end result is ATP. And other things along the way. The ATP is the main thing. Okay. Now, if we think about a molecule of ATP, that's the energy molecule that powers our body, chemical reactions. ATP is held together by chemical bonds. Any chemical is. Okay. Glucose is. And it's in the chemical bonds where the energy is stored. Okay. I mentioned this yesterday if you're in lab. Chemical energy is stored in the bonds of any molecule. All right. So it's just a little bit of an intro. I thought this picture on this magazine was a little bit interesting because it talks about fuel your body for optimal performance, because we think of chemical energy, sometimes we refer to it as fuel, the fuel for our body. What fuel do we give our body? Food. We fuel our body with food and oxygen, right? We have to breathe oxygen. And both of those things are essential for doing all of our metabolism and harnessing energy to do work, okay? So This is where we're going to get to kinetic and potential, because we're going to talk a lot about potential energy. Okay. Energy stored in chemical bonds is potential energy, right? This is stored energy, right? Just like a big dam that you would see holding water, a hydroelectric dam, it's storing up a bunch of water. It's got a ton of potential energy that once it flows through the dam, it then creates the movement needed to power the dam and create electrical energy. Okay, how's that different from potential, or sorry, how's that different from kinetic energy? Kinetic energy is the energy of movement, okay, of motion. That's energy in motion. All right. So we are mostly going to be, yeah, you're good, movement. Okay, so we're mostly going to be talking about potential energy, stored energy. So keep that in mind as we move forward. And then energy can freely, lastly, I'll say energy can freely flow between different forms. Okay, so we don't create energy, we don't destroy energy, just like we don't create or destroy atoms. It just transfers between different forms, right? So that gets us to this slide. And the main question we're going to ask today is on this slide. How do we know if a chemical reaction is going to happen? We've spent a lot of time in chapters 5 and 6 addressing how to write chemical reactions, how to balance them, how to classify them, how to understand them. But now we're going to say, how do we know if it's going to happen or not? Just because you mix things together doesn't mean you're guaranteed a chemical reaction, right? Look at this one on the slide. We have AU. Anybody know what AU is? Chemical symbol for, it's for gold. We've got gold and we've got water. Let's say I had a gold ring or a gold necklace, and you drop it in a cup of water. Are you guaranteed a chemical reaction? We could write products for it. You see some products here. We could balance it, but you're not going to see a reaction, right? If it is, it's going to be really, 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 really slow over maybe years and years and years, okay? So again, that's the point I want to make. How do we know if reaction is going to occur? And I'm going to use this word spontaneously. Okay. Now you guys think of spontaneous as, oh, I'm going to get up and travel across the country today. That's spontaneous, right? Like something that's just like abrupt. But spontaneous in the definition of a chemistry reaction is a little bit different. Spontaneous means something that once it gets started on its own, it's just going to go to completion. Okay. Once it gets started on its own, it's going to go to completion. So how do we know if a reaction will occur spontaneously? And how do we know if it will run on its own? Well, energy. Energy determines if a reaction will occur spontaneously. And I'll tell you, this is layered, okay? There's not one straight answer. There's not one quick answer on this. So we're going to learn, it's like a 3-piece puzzle when it comes to this whole idea. And we're going to look at piece 1 and hopefully piece 2 of the puzzle today. So here's a really important statement. If the products in a chemical reaction have less potential energy than the reactants, then the reaction will occur spontaneously. It will run on its own and it will go to completion. All right. So I want to talk about this idea really quick. I'm going to zoom in. Hold on. I'm going to let everybody write this down. Fill in your blanks. Less potential energy. I'm going to draw a little energy graph really quick. I did this yesterday in lab and I think it helped. So if I have a little energy graph, just like this, and my y-axis is energy. Let's say I have some reactants. I'm going to put an R for reactants. And they have this amount of energy, okay, just corresponding to that amount. And again, I'm not giving it any sort of number. This is all arbitrary. But then let's say my reaction goes and I end up with products that are lower in energy. They have that much energy. These products have less potential energy. That's what we're talking about right up here, less potential energy. That's a favorable reaction. Why? Because the products are more stable. Things with less energy are more stable. I'm going to say that again. Things with less energy are more stable. That's favorable for our bodies, okay? Our bodies do have to run reactions that require an investment of energy, but their favorite kind of reactions are reactions that give off energy, okay? And you make products that are more stable, all right? Is that less potential Yeah, less potential. So you could write potential energy. So yeah, we're talking about potential energy. All right. So like I said, 3 factors, 3 pieces to the puzzle today determine the energy associated with our reaction. So the first piece is going to be enthalpy. Enthalpy. The second piece is going to be entropy. And then we've got Gibbs free energy. And I just want to ask really quick, who's heard these terms before? Oh, sorry, in the chat. Why would we want that if we want more energy to use? Well, Bailey, the reason is we want to run, our body likes to run reactions like this because these kinds of reactions in the difference here, between here to here, we give, whoops, off energy. And that energy is used to do work. Our body has to run billions and trillions of chemical reactions every single day. We have to constantly be getting nutrients to cells and getting rid of waste, and all of that takes energy. So we have to run reactions like this that give off energy so we can do work in the body. Does that make sense? If we're constantly running things the other way, we do have to make reactants that have lots of energy, but we have to constantly break them down so we can get the energy extracted out of them and go do work for our bodies to stay alive. I hope that makes sense. Okay, so anybody heard these terms before? Enthalpy, entropy, Gibbs free energy? You can just nod your head. Give me a thumbs up. Give me a thumbs down if you haven't. I kind of want to know. Okay, good. So this is brand new for some of you, maybe a lot of you. And we're going to start with just enthalpy. So what is enthalpy? To introduce the idea of enthalpy, I'm not going to define it just yet, but to introduce the idea of it, this is what we talked about. Again, if you had lab yesterday, reactions occur via the rearranging of bonds, right? We don't destroy atoms, we just rearrange them in a chemical reaction. And when that happens to rearrange things, we have to break bonds on the reactant side, we have to form bonds on the product side. We have to break bonds on the reactant side. So the breaking of bonds requires an investment of energy. It costs us, our bodies, energy to break bonds. And then forming bonds or making new bonds, which are your products, right? That releases energy. So any chemical reaction, we always break bonds on the reactant side. And we form the new bonds on the product side. Right? Okay, so the question then becomes, well, how much energy are we talking? And the answer to that is it depends what kind of bonds you're trying to break. Okay, so different bonds require different amounts of energy. So it depends on a couple things. One, what atoms are involved in the bonds and how strong is that bond? And then 2, how many bonds are holding those atoms together? Is it a single, a double, or a triple bond? Okay, it probably makes sense that it's going to cost us more energy to break a triple bond than to break a single bond. Okay, and here's an example, in case you don't believe me. I've got 2 molecules right down here, a nitrogen molecule and a chlorine molecule. Nitrogen is held together with a triple bond. Chlorine is held together with a single bond. You can see, here's in red, the energy numbers. It takes more energy to break which bond? Remember, units of energy are kcals and kilojoules. Y'all are not very responsive today. Takes more energy to break the triple bond. Okay, that one has the higher number. So what we say, we call this a bond dissociation energy. How much energy does it take to disassociate those atoms? Is anyone reading the chat? Anyone having awful internet, consistently breaking up? Are y'all having trouble hearing me? Some people are shaking their head no. A few of you are. Okay. If it's to the point you just can't understand me, then feel free to watch the recording, but please stick around if you can, power through it so that you can take notes live. I think that's going to be important.
Yeah, right quick. Could you scroll back up a little bit?
Okay, so going back to this idea is we call it a bond dissociation energy. All right, and that's again just the amount of energy that it requires to break different atoms apart. Okay, so you can see for breaking apart the chlorine molecule, it takes, like 1/4, less than that, 1/5 the amount of energy. Okay, so anyways, we call these bond dissociation, and it also gives you the number in kilojoules, and it's per mole of molecules, and we know a mole is a really big number. So I think that's what I just said down here. The amount of energy necessary to break a bond. This is sometimes we'll abbreviate it BDE, but it's the bond dissociation energy, abbreviate energy. And sometimes you'll see this BDE. Okay. So that's kind of the basis of this idea for enthalpy. And we're going to look at a couple of examples. We're going to work a few things out, and that's what the lab is about all this week, your enthalpy practice lab. So this table is going to be really, really handy for us as we do some practice problems, and on the lab, you're going to have this table, and you will have this on exam 3. You'll have this table on your resources page. So this is a whole table of bond dissociation energies. It's not all inclusive, okay? It doesn't have every bond in the world, but we're only going to use bonds on this table, okay? If I give you another kind of bond, I'll give you the bond dissociation energy. You'll probably also need this for the quiz on Thursday, all right? So have that readily available for your quiz Thursday. One thing I want to point out, I'm going to highlight this, is right here. Do you notice there's an asterisk on this carbon-oxygen double bond? So that takes us right down here. So it says the CO bond dissociation energies in carbon dioxide are different numbers. Why would they be different? And I don't know exactly why they're different, but they are. So any carbon-oxygen double bond, you use 178 up on the table. But if it's specifically CO2, a molecule of CO2, then you have to use this table under here, or this number down here under the table, 191, okay? Or the number in kilojoules. Okay. All right, so also I wanted to just make sure you know how to read this correctly. This first column, okay, all the bonds here, these are the numbers associated with them, okay? Then the second column, these are the numbers associated with them. And then the third column, these are the numbers associated with them, okay? And it gives you both the kcal and the kj kilojoule value. So always make sure if I ask you to report it in kilojoules, make sure you use the kilojoule values. If I ask it in kcals, on the lab, you're gonna do everything in kcals. So anyways. All right, I also wanna make the point, so this is the same figure on this slide from above with the nitrogen and the chlorine molecules. I just wanna make the point that forming bonds and breaking bonds, if it's the same molecule or the same bond, it's just the same process in reverse, okay? So if breaking these bonds right here requires energy, then when you form these bonds, which is these reactions down here, 2 atoms coming together to form the bond, it releases energy, okay? So when we form bonds, we release energy, we can write that energy as another product. You guys see this? This is really, really important what I just said, because there's gonna be times where I ask you, is energy a reactant or a product? When you form bonds, so we're doing right here, energy is released. And so we can write the release of that energy as a product, okay? We make this molecule plus we make that amount of energy. And we don't make it out of nowhere. We're just releasing it from the forming of that bond, okay? So if energy is a product when you form bonds, guess what? Energy is a what when you break bonds? It's a reactant, okay? If it's a product when you form bonds, energy is considered a reactant when you break bonds. All right, this is called the law of conservation of energy. And this is what I mentioned earlier, but energy is neither created or destroyed, just transferred between all kinds of forms, mechanical, chemical, a lot of the different forms we named earlier, thermal. So the whole point of this slide is that the energy required to break a bond is blank as in is the same as as the energy released in making that bond, all right? Because they're just reverse processes. Okay, so I think we're now going to define what enthalpy is, and we're going to practice some problems calculating enthalpy. Do I need to stay on this slide for a minute? Everybody good?
Yes, I need to write it down right quick.
All right, so you're going to want a calculator on the next few of these slides, so grab that if you have one. We got some poll questions coming up after some practice problems. Okay, you good, Glenn?
Yeah.
All right, so enthalpy is a measure of the energy stored in reactants and products, okay? So for any molecule, we could say this molecule has that much enthalpy based on what bonds it has. And the bond dissociation energy, we could add that up for any molecule. And we're gonna do that. Now the change in enthalpy, this is the difference between the energy needed for bond breaking and bond formation across a reaction. All right, now by the way, we abbreviate enthalpy with an H. And we abbreviate, I meant to leave space for this. We abbreviate change in enthalpy. We use the Greek sign delta, and we use an H. Change in enthalpy. So the lab is all about calculating this right here, delta H. You'll hear me say that, delta H. What's the delta H? Is the delta H positive or negative? Okay, we're gonna talk a lot about that, change in enthalpy. So let's look at this reaction right here. N2 plus hydrogen, H2 makes ammonia, NH3, and it's already balanced for you. So we want to calculate the delta H for this reaction. How do we do that? Okay, so the first step one is you got to have a balanced reaction. 2, draw your Lewis structures. So step 1, you need a balanced reaction. And step 2, you need Lewis structures, because we're trying to think, okay, what kind of bonds do we have here? What kind of bonds are we breaking? What kind of bonds are we forming? So to see that, we need the Lewis structure. So a molecule of nitrogen is right down here. So I'm just going to draw that. And according to this reaction, in the balanced reaction, how many moles of these nitrogen molecules do we have? According to the coefficient on the balanced reaction, just a 1. Okay, so I'm just going to draw 1. Now a hydrogen molecule looks just like this. And according to the coefficient on the balanced reaction, how many moles of hydrogen molecules do we have here? 3. So I'm going to draw all 3. Because we have to break every single one of these bonds. So to break this bond right here and to break all of these, how much energy is it going to cost us? Because remember, breaking bonds requires energy. Breaking bonds requires energy. So I have the numbers right down here. Okay, so we need to add all this up. I want the total number. How much energy total do we have to invest on the reactant side to break all of these bonds? So each nitrogen triple bond cost us 226 kcal per mole. And each hydrogen single bond cost us 104 kcal per mole. And we got 3 hydrogen single bonds to break and 1 nitrogen triple bond to break. So what you should do is 226 kcal per mole plus 3 times 104 kcal per mole. Anybody have the total for us?
38.
Okay, thank you. So we're going to call this the enthalpy of the reactants. And that equals 538 kcal per mole. Okay? That's the enthalpy of the reactants. It's going to cost us that much energy to break every single one of those bonds. On the product side, we have what's our molecule? What kind of bonds do we have? We have NH3. So we know NH3 looks like this. And how many moles of NH3 molecules do we make? 2. So you could draw out both if you want. And as you go, as you practice more with these, you don't have to draw it out, 2 times or 3 times or 6 times or whatever your coefficient is. You can just draw it once, but you do have to factor in your coefficient. Okay, you have to multiply the number of bonds in the molecule by that. So here in one molecule of NH3, I'm going to highlight how many nitrogen, hydrogen single bonds do we have in just one molecule?
3.
3. There they are. 1, 2, 3. And guess what? We have 3 more down here. 1, 2, 3. Okay. So I've already accounted for my coefficient because I drew out both molecules. But if I only drew out one molecule, I would have to do 3 times 2 to get the 6. Gabby's asking me a question from the lab. Say you have C3H8 and C3H7Cl with a coefficient of 1. Then yes, they're just multiplied by 1, Gabby. You got carbon-carbon bonds in those molecules, you got carbon-hydrogen bonds, and you got a carbon-chlorine bond. So you got to account for all the different bonds. Yeah. All right, so here, what is the nitrogen-hydrogen bond dissociation energy? It's right down here. It is 93, okay? So we're going to do 93 times 6. Okay, 93 kcal per mole times 6. And this is going to be the enthalpy of the products. Anybody have that total for us?
558.
558. Right. All right. So we just did a lot of work here. You can see how layered this is. Getting this right, getting things in chapter 7 right, depends on getting things in chapters 5 and 6 right, and getting your Lewis structures right, which is chapter 4 stuff. Okay, so you can't forget anything we've already done in this class. All right, so I'm going to pause there. Let's go to the next slide. We calculated our enthalpy of reactants and the enthalpy of products, okay? And you actually see these values right down here. Okay, so this much energy, 538 kcal, that's how much we need to break all the bonds. 558 is how much energy is released when we form all these new bonds. So how do we solve for delta H? I'm not going to fill these things in. That's just from the previous slide, enthalpy and change in enthalpy. How do we solve for delta H? What you do, delta H is this equation. It is your enthalpy of your reactants minus the enthalpy of the products. And you'll see equations in the book maybe that have this little Greek symbol, this like sigma right here. This just means the sum. Which is what we did when we added up everything on both sides, okay? So we're just gonna take these numbers and subtract them. What's 538 minus 558?
Negative 20.
Yeah, negative 20, okay? We did that right? 38 and 58, okay. So we get negative 20 kcal per mole. All right, so we just solved for a delta H. Okay, now what does this mean? What does this number mean to us? Why is it important? Here's what it means. Overall heat is released when overall heat is released, and that's what you see when this number is bigger. More heat is released. So overall, we have a negative 20. Delta H is negative. When you have more heat released on the product side, overall delta H is negative. If overall heat is absorbed, I don't know if I spelled that right. There's a P in there, right? ABSOR. Okay, it's supposed to be absorbed. But if it's overall absorbed in the reaction, delta H is positive. If someone wants to respell that for me, go for it. All right, so that's a little bit on delta H, and that's an example of calculating delta H. Okay. Here's another example where we have nitrogen and oxygen coming together to form a molecule of NO. First, before I move on, I want to go back here. Any questions on what we did up here? If you do have questions and you're not sure what to ask, we're about to work through one more example, and that may click more things in place and may clarify anything. So we have a molecule of nitrogen, and you see the bond dissociation energy there. This is balanced already, by the way. So we got coefficient of 1 here. So we don't have to multiply this number by anything. Multiply by 1 if you want, right? We got a understood 1 with oxygen. And so we don't need to multiply this by anything as well. That's the bond dissociation energy for the oxygen molecule. And then we've got 151 for the nitrogen monoxide. But we have 2 of those, so we do need to multiply this by 2. Okay, because of the coefficient of 2. All right, so you're maybe seeing here, you've got to account for the number of bonds within a molecule, and you have to account for the coefficient. Both matter. You've got to account for both and multiply those things when you're trying to figure out the total number of bonds, okay? And add everything up. So what's our total heat input? How much heat or energy do we have to invest to break all the bonds on the reactant side? 226 and 119.
345.
Oh, you said 45, right? And then the heat output, 151 times 2 should be 30. Is that 302?
Yep.
All right. So then when you take the difference here, 345 minus 302, you get a positive, your delta H is positive 43 kcal. So 43 kcal per mole more energy is needed for bond breaking than what is released in bond formation for this reaction. So this one's different than the one we did on the last slide, because here the delta H overall is positive because we needed more energy on the reactant side to break all those bonds. Okay, so overall heat input is needed. All right. Oh, I think I meant to do that down here. 345 minus 302. All right, that's where we got the positive 43. Okay, these were statements that we set up above. Just kind of repeating myself because that never hurts to do. When heat is released, delta H is negative. When overall, the difference on the two sides, heat is absorbed. Look at that. I did spell it right. In the reaction, delta H is positive. Okay. Again, questions so far? There's our table again. All right, I'm going to introduce 2 vocabulary words. These are the 2 reactions we did. We did this one up above, and then we did this one just previously. So we saw on this first one, we had a negative delta H. On the next one, we had a positive delta H. So if delta H is negative, the reaction is, oh, sorry, I see a question in the chat. It confuses me. I feel like it should be opposite. I'm reading the chat. Like if heat is released, why wouldn't it be positive? Well, health science major doubt any of us are good at spelling. Thank you, Rachel. Because there's energy coming off, right? Okay, Bailey, the reason why it feels backwards, I'm actually glad you point this up, is because you're viewing it from our standpoint. We're the surroundings. We're trying to actually view this from the standpoint of the chemical reaction, okay? So you kind of have to like step inside the chemical reaction and say, if I'm the chemical reaction, if I'm giving off energy, I'm losing energy, okay? This sounds weird to do, but when you're viewing it from the standpoint of the reaction itself, if it's releasing energy overall, it's losing energy. So from the viewpoint of the reaction, the energy loss is negative, okay? Does that answer your question, Bailey? And I'm going to get to that again the more we talk about this. Okay, good. And if you're absorbing energy overall, that's why the change in the delta H is positive, because you're gaining energy. All right, so sorry, going back to this, we're going to fill in, these are kind of like vocabulary words. If delta H is negative, it's exothermic. And if delta H is positive, we call this endothermic. Okay, so we got exothermic and endothermic. If you did an exothermic reaction in a test tube, how would it feel to you? Do you think it would get hot or get cold?
Hot.
That's correct. It would get hot. Endothermic would get cold. Okay. Because it's absorbing energy, absorbing heat, we would feel the loss of heat from the surroundings that's going into the reaction. All right, we got a poll question here. I'm going to launch this. Here's the question. Are these reactions exothermic or endothermic? So there's 4 different questions here, so make sure you put your answers in for all 4. Based on what we've talked about, heat being a reactant or a product, your delta H being negative or positive, are these exothermic or endothermic? Oh, Riley, I will scroll up in just a moment once we get done with the poll. All right, I'm gonna give you about 20 more seconds. We're gonna go over these. So if you're just not sure, that's okay for now. All right, 10 left. Go ahead and get your answers in. All right, I don't see it going up anymore. I'm gonna end the poll. Share results. Okay, so for number 1, most people said exothermic. And that is correct. This is exo because heat's a product. Okay. Number 2, most people said endothermic. So heat as a reactant, it comes before the arrow. So it's just the opposite of the first one, right? If it's a product, it's exothermic. If heat's a reactant, it is endothermic. All right, number 3 and 4, you're not given heat written into the reaction, but you are given the delta H. So most people said number 3 is exo. Got a negative delta H. And that's exactly what we said just up here. If it's negative, it's exo. So that's good. It should have been exothermic on number 3. And on number 4, you just have just the opposite reaction. So this one you had A plus D making AD. The 4 is opposite. So if this one is exo, then this one has to be endothermic. All right, I'm going to scroll back up. Riley wanted me to scroll back up for just a second. So there's more slides I'm pretty sure that I have for practice problems here. And we're going to look at one other poll question, but then we are going to spend the remaining time of class looking at puzzle piece number 2 to try to make up some lost ground from snow day stuff and the fact that I cut a lecture day out. Are you good, Riley? Okay. So a few more practice problems and then we're going to move on. Another style of question you're going to have to do on the lab this week. Let me stop sharing the poll. Is something like this right here. So a lot of times you'll be given, and like on the exam, I'll give you a reaction. I may give you the delta H, and then I just may ask you questions about this or have you do a small conversion on it. And just like you're used to pulling out relationships from like a word problem, we can pull out relationships this time with energy. Okay. So this is balanced, or it should be. Yeah. 1, 2, 1, 2 on our coefficients. First off, is this endothermic or exothermic? What do y'all think? Based on your delta H. You should just be able to look real quick.
Exo.
Yep, it's negative, so it's exothermic. Now we're going to do a little bit of calculating. How much heat is released? Scenario A. If we do a reaction with 0.35 mole of CH4, this is methane. 0.35 mole of CH4. So in the balanced chemical reaction, here's what I see. For every 1 mole of methane, we produce negative. We got a negative, so we produce 213 kcal. So I'm going to write that reaction out, or that relationship, sorry. For every 1 mole of CH4, that corresponds or is related to 213 kcal. And you don't have to do the per mole part here because you've already got the per mole on this side, okay? So if I only have 0.35, if I have a third of that, how much energy do you think I'm going to produce? This is a ratio, so we're going to keep this ratio the same. You can use this as a conversion factor. So you could actually write this, I'm going to zoom in, as 1 mole of CH4 per 213 kcal. And then we can decide if we need to flip it, which one we need on top or which one we need on bottom, to cancel moles of CH4 and convert to kcal. So we're just use this just like a conversion factor. So start with the number that you're given in the problem, the 0.35 mole CH4. And use your conversion factor. We need to flip it because we want to cancel moles of CH4. So for every 1 mole of CH4 that we put into this reaction that we have, we're going to produce 230. Oh, sorry, I don't know what happened. There we are. We're going to produce 213 kcal. Okay. Well, it's just asking how much energy total. So if I ask you about the direction of the energy, like is it released or absorbed, you could include the negative. But here, I'm just asking you kind of the quantity of energy. So that's why the negative doesn't matter. Sorry if that's confusing. But actually the negative does not matter here because I'm just saying how much energy. And so the negative or the positive, we're just asking kind of the absolute value of it. So you do 0.35 times 213. What do y'all get?
74.55.
kcal. Okay. So there's going to be one problem on the lab you have to do like this. And then this one, if you start with 7.5 grams of CH4, all you have to do is convert this to moles first, and then you do the same thing we just did. So this one just has an added step. You get the molar mass of CH4 and convert grams to moles, and then you use the same conversion factor, convert moles to an amount of energy. Okay. So molar mass of CH4, we got 12.011 plus 4, that's the carbon, 4 times the 1.008. I'm just going to say 0.01. And so that's 4.04 plus the 12.011. Grand total, we get 16.051 gram per mole. All right, so then we take our 7.5 grams of CH4, convert it to moles. So plug your grams down here on the bottom, 16.051 grams of CH4 per 1 mole of CH4. Then use the same conversion factor. That's going to go in right here again. I want to cancel moles of CH4, so for every 1 mole of CH4, it's 213 kcal. So you do the 7.5 divided by the 16.051 times the 213. And I left no room for my answer. What do y'all get?
I'm kind of confused on this one. But
Thank you. Okay, good. Well, not good that you're confused, but thank you for asking your question. So on this one, Glenn, I bet other people are confused. We started with grams of CH4 instead of moles. Okay, so in the previous one, we started with moles of CH4. So because of that, we're actually going to go back to, so this is some stuff we learned from chapter 6. Anytime you're trying to convert from grams to moles, you have to use molar mass. Okay, so that is why we calculated the molar mass of CH4 right here. This was the carbon and this was the hydrogens. And we added up, multiplied by the number of hydrogens that we had. We had 4 hydrogens, 1 carbon. So we got the molar mass right here. And we used the molar mass. Remember, molar mass lets you convert between grams and moles. So we took the grams, converted to moles. And the question is still this up here. We're still answering this question. How much heat is released if we only have 7.5 grams of methane, the CH4? So first we had to get it to moles, and then from the balance reaction, we looked up here at the coefficient. We said for every 1 mole of CH4, that is associated to my given delta H, which is 213 kcal. Okay, so that's where we wrote out, I'm going to highlight this relationship right here, and we plugged that in over here so that moles of CH4, I'll show you, grams cancel, I'm on highlighter. If I have one thing you can quote me on, it's always, oh, I'm on highlighter. You cancel moles of CH4, grams of CH4 and moles of CH4, and then you end up with your amount of energy. So that's what people are typing in the chat. 99.52 seems to be like the answer there.
Wait, so you would do like 7.5 divided by 16, and then times 213?
Yep. Yes, this 16 right here is on the bottom. So anytime things are on the bottom, you divide by them. Anytime they're on the top, the 213 is on top in the next conversion factor, you multiply by that. So 7.5 divided by the 16. I know there's a time symbol here. I'm going to point an arrow to it. Those are time symbols, right? But if it's times 1 over 16, that's the same as saying divided by 16. Okay.
Okay.
All right. Okay, I have one more poll question regarding this statement that you see underneath. So based on everything we just talked about so far, fill in the blanks. In an exothermic reaction, the products are they more or less stable than the reactants? And then does this make the reaction favorable or unfavorable? I'm actually not sure I directly talked about something being favorable or unfavorable. If something is spontaneous, it's favorable. If it's non-spontaneous, it's not favorable. If something's going to be more stable, if the body's making products that are more stable, that's going to be favorable. If it's making products that are less stable, that's not going to be favorable.
I'm sorry, can you say that one more time?
If the body is making products that have less potential energy, lower in potential energy, that's favorable. If it's making products that are higher in potential energy than the reactants, that's unfavorable. All right, there's only 5 people left. Looks like we about got all answers in. I'm gonna end the poll. Share results. Oh, I'm glad we are looking at this one. We got a 50-50 split almost on 18 people pick more, 19 people pick less. Okay. In an exothermic reaction, the products are they're more stable. They have less energy. I almost mixed myself up. Let's go back. Remember that energy chart? I'm going to scroll down here where I have some space. Remember that energy chart we drew? This potential energy. If your reactants are here and your products are here, this is an exothermic reaction. Okay. This is what an exothermic reaction looks like on an energy diagram. Okay, because you are, as you go, you are giving off energy, the reaction is. So your delta H is negative. So the products have less potential energy. But what does that mean regarding stability? They have less potential energy, but if you have less energy, you are more stable. This is what we wrote on the slide way up earlier. So they're more stable. Less potential energy, less energy means you're more stable. Okay, so that one was actually kind of tricky. So you should have picked, let me go back up here. That it's
Okay,
more,
so it's favorable to be negative.
yes, that's what I'm getting to, Kristen. This makes the reaction, oh, well, I gave you the answer on that one. You turkeys, I didn't realize that. Okay, so they're more favorable. So yes, that's what we're getting to. That's the whole point of what we've talked about so far. I want to recap. I'm just going to use this blank space down here. A negative delta H, which is exothermic, this is favorable to the body. Why is this favorable to the body? Reactions that give off energy provide energy for other reactions to happen. Remember, your body's doing millions, billions, trillions of reactions all the time. Metabolism, breaking down food, building components that our cells need. So reactions that give off energy in the form of heat. Okay, you have to maintain body temperature too. Anybody put your hand right back here, like on the back of your neck, you feel kind of warm. You're maintaining body, you should feel slightly warm all the time. Okay, so you're a giant exothermic reaction walking around. Part of that heat given off in these reactions is used to maintain body temperature. But a lot of the other energy is used to power other chemical reactions. So that's why this is favorable to our bodies. Okay, I hope that makes sense. All right, so as I mentioned, there's more review questions here, and I promise we're going to spend some time doing review before exam 3, and I'll probably come back and grab some of these questions. So I'm going to jump over this slide right here and the next slide right here, even though there's another practice problem, because we got 10 minutes left in class, and I want to talk about the next puzzle piece, okay, which is entropy. So we've said so far negative delta H, which is favorable, and positive delta H, which is unfavorable. That's essentially the review so far, sum total. And by the way, I need to mention this. We use the word spontaneous. I'm just going to abbreviate SP to talk about things that are favorable, and non-spontaneous to talk about things that are unfavorable. You can use those interchangeably. So I wanted to mention that because now I want you to read this little question here. Are all exothermic processes spontaneous, or you can say favorable? And all endothermic processes non-spontaneous, meaning unfavorable. So just because this is what we learned so far, can we say all processes are like this? Well, I want you to consider the statement. If you set ice out on a plate, you take it out of the freezer, you put it at a plate at room temperature, it will absorb heat and melt. It will absorb, oh, I need to stop sharing the poll. Sorry, I'm catching up with the chat. Heat release it, which is good, yes. Sorry, Bailey, I'm coming back to your question. Can you go over the relationship of exo-endothermic and where heat is a reactant compared to that, to favorability? Okay, I'll add in here. Oh, I did already, okay. All right, so if you set ice on a plate, absorb heat and melt. Okay, so let me ask you this. When you take ice out of the freezer and you put it at room temperature and it starts absorbing heat, key word here, absorbing heat. Things that absorb heat, is that an endothermic or an exothermic process? Chelsea said it. This is endo. Now let me ask you this. Are you going to have to pop that ice in the microwave or put it on the stove in a pot and turn the heat on? Or is it just going to happen spontaneously? This will be spontaneous, right? You aren't going to have to do anything. Now, technically, you put it in an environment with a warmer temperature, okay? But you didn't have to do anything else. You didn't have to add any sort of heat to it. So what we have here is we have an endothermic process that's spontaneous. So essentially, everything that I set up here, I kind of just usually, this is the case, that exothermic processes are spontaneous and favorable. But remember in chemistry, never say never, okay? Never say always. There's usually exceptions, all right? We have an endothermic process. That's a very common one that we can understand that's spontaneous, all right? So I want you to adhere to these things. I want you to know these things, and we go by these things, but there's an occasional exception. And so what that means is there must be more to the big picture, okay? To answer some of these questions about when will reactions happen and occur and why and how with energy. So that brings us to puzzle piece number 2, which is entropy. All right, so hang with me. I know we got only like 7 minutes left of class. Y'all are doing great. We're almost there. Entropy, okay? We abbreviate entropy with an S. This is a measure of disorder in the system, okay? Disorder in the system. Remember, the system is this is your reaction. We are viewing things from the viewpoint, from the standpoint of our chemical reaction. Okay, our system is reaction, reactants and products. So again, if we have delta S now, delta, the Greek symbol change, this is the change in entropy for a reaction. So for delta H, we had units. Let me remind you, delta H, we had kcal per mole, or it could be kilojoules, kJ per mole. But what you see for delta S is something a little different. You have calorie per mole, and you have a little k here. What does this k stand for? What does K stand for in the past? Anybody remember K? Thank you, Emily. This is Kelvin. So this is a temperature. Why do we have a unit of temperature in this overall unit for delta S? Okay, so there's two differences. If you're looking between delta H and delta S, the main differences are one, we have calories, not kcal. Why is this? Okay, the reason for this is that changes in delta S tend to be a lot smaller, okay? That doesn't mean they're not important or not significant, but that's why we use a smaller unit, okay? A calorie is the same unit, just 1,000 times smaller than a kilocalorie. And then the K on the bottom here is, so we have a unit of temperature. So that means that delta S is temperature dependent. All right, temperature dependent, because we have a unit of K for Kelvin in our delta S. All right, really, really, really important. So once you understand those two differences in the units, processes for which delta S is positive, meaning this, as you go from your reactants or products, you're becoming more disordered, okay? So as the reaction happens, you are growing in disorder. Anybody, as your day goes on, your house just becomes more and more disordered? I have 2 kids at home. I literally vacuumed my house. Like, I mean, I even pulled out my refrigerator and vacuumed my house Friday night. Anybody do that? And then Sunday, it's just like there's Cheerios all over the floor. It's a crazy mess, right? So as we live, there's funny pictures you can look up on the internet. Life tends to become more disordered, all right? So we're very familiar with disorder. Same idea with chemical reactions. When you have a reaction that's becoming more disordered, processes for which delta S is positive tend to be spontaneous or favorable. Okay, so we've learned the negative delta H is the favorable one, but the positive delta S is the favorable one when it comes to entropy. Okay, are things complicated enough for you yet? All right, I think we got time. This is going to be the last slide we go over, this next one. Last slide, and this is probably all we're going to get to today. So questions so far on disorder and entropy. I'm about to explain how you assess disorder in a reaction. Some of you are like, I already have enough disorder in my life to assess. Thank you. Okay, these statements are kind of obvious, I think, but I have them typed out anyways. So when you have a positive delta S for a reaction, entropy in that reaction is increasing. A negative delta S, entropy is decreasing. Let's look at this reaction right here. We actually drew out this one earlier. This is the formation of ammonia. You got the nitrogen molecule and the hydrogen molecule, and you're making NH3. So here's what I noticed too. We're given the abbreviations. Remember what these stands for? This stands for the physical state. This is a gas. This is also a gas. This is a gas as well. Okay. So this is going to be important. The physical state, the abbreviation for those in your reaction, that's going to be important for you determining entropy for reactions, okay? So this figure right here is key. This is in your textbook, and this tells you how to assess entropy for any reaction and then determine if your delta S is positive or negative. So if we are looking at the physical states here, this top kind of line, as you read this figure from left to right, entropy increases. Okay, so what that means is as you go, if you have reactants that are a solid and you're making products that are a liquid or products that are a gas, or if you have reactants that are a liquid and you're making products that are a gas. Regardless, there's so many ways you could dice it up, so many different examples I could give. But if in general, you're transitioning from solids or liquids towards liquids or gases, you're increasing in disorder. You guys remember when we drew the, this was way early in the semester, when we drew out how these look? Okay, the molecules in a solid are close together, they're packed together, they're not moving a lot. Liquid molecules, they're a little further apart and they're fluid, so we drew arrows. Gas molecules, they're really far apart and they're zooming past one another really fast. There's more disorder inherently in the physical state of a gas than a solid or a liquid. Solids are very ordered. So as you go from solids to liquids to gases, you're increasing in disorder. All right, last thing, because we're at time. Entropy decreases if you read it from, wait, I missed this last one. Fewer moles to more moles, okay? If you have like 1 or 2 moles when you add up all your reactants, so you're looking at your coefficients, and you have more moles of stuff on the product side, obviously you're increasing in entropy. And then the process is reversed if you read the reaction right to left. So if you have more moles on your reactant side and you are making fewer moles on the product side, entropy is decreasing, okay? So fewer moles to more moles, this would be like a decomposition reaction, okay? But more moles to fewer moles is like a synthesis reaction. That's what you have up here. You got 1 mole plus 3 moles of gas. So total you got 4 moles of gas. And over here you only have 2 moles of gas. So you're going from 4 moles down to 2 moles. Okay, and everything's a gas, so we really can't assess changes in physical state. So entropy here is doing what? It's decreasing. You're becoming more ordered. All right, I've gone over time. I think your brains are all busted so far today. So I'm gonna leave it at that. If you have questions on any of this stuff, we're gonna pick up with Delta S on Thursday and keep moving. And then I'll probably have to post a video lecture on like some stuff later on. Thanks for joining today. I've got office hours at 9:30. Please join me if you can. If I need to go back to this slide, I will. Just let me know if any of you are still writing. Any questions from anybody? Bye, Whitney.